Hello, everyone. This is Spencer Snolling from Hydromantis, and I'm glad that you could join us today for our continuing webinar series about GPSX. I also have my colleague with me today, Dan Song, who will be presenting a case study about a lagoon modeling project that we did earlier this year. So thank you for joining us. It's the same sort of situation as we always do with these kinds of webinars. We want you to be able to learn a little bit about what's in the software and get a little bit of an experience about some of the projects that we have worked on. So today we're going to be talking about lagoons and ponds using that sort of treatment technology and how you model that in GPSX, because it's a little bit different. And there's a little bit of a different approach to doing that for these systems. So like any of the webinars that we have normally done, our plan is that for the next half hour or so, Dan and I will be doing our presentation and showing slides and so on. In your GoToWebinar dashboard, you will find a questions box, and you can type in any questions that you have there as we go along. And as part of that, what we'll do is we'll collect up all of those questions, and at the end of the webinar, we will stick around and answer a few of those, as many as we can that we have time for. So go ahead and open that up, and if you have anything that you can think of that you'd like to know more about, just type your question in there. Okay, so let's get things rolling. So as I mentioned, modeling lagoons and ponds, and just for clarity, I'm going to use those two phrases interchangeably here. I'm going to mostly refer to these things as lagoons. Lagoon treatment for wastewater is a somewhat more challenging thing to model in GPSX because there's somewhat more complexity around the idea of trying to figure out what's actually going on in those types of systems. So what we're going to do is I'm going to talk about a number of different techniques and important things that you're going to need to think about and information you're going to need to collect in order to be able to model them in GPSX successfully. And then, as I mentioned, Dan will come on and talk about a case study. We did a project where we built and calibrated a model of the Northwest Langley wastewater treatment plant, and they have a lagoon right at the very sort of front end of that process. And so we'll talk a little bit about that and our experiences and how we built that model, made some decisions about what we needed to know, and then calibrated it. So in the end, we'll kind of summarize up all these different techniques and things that you needed to know. And then, as I mentioned, we will go right into any questions that you might have. Okay. So lagoons are essentially large treatment reactors of varying degrees of technological complexity. So you can see this one that I'm showing in the picture here is obviously something with a poured concrete base. But of course, a lot of lagoons and ponds are, just large dug holes that you fill with wastewater, or they may have, an engineered liner or what have you. But there's a lot of different types of technology and levels of treatment that are sort of collected under and referred to under the umbrella of lagoons. So some of these systems can be just completely on their own. They're just a large anaerobic reactor and settler, or they can actually have fairly complex aeration systems and mixing systems and control of the flow in those things. So it becomes a little bit more complex problem when you want to try and model that sort of a system. So the models, or pardon me, the lagoons themselves can be really quite simple in terms of, shallow pits that are really there just to do some like polishing and maybe settle out some final solids. And as I mentioned, some of them can have, very sophisticated aeration systems, on par with what you would find in a full-scale BNR plant. And these are, common throughout the world, and they're used in both the municipal and industrial wastewater treatment world. So the problem with trying to model a lagoon is it can be sort of a simple idea and a very complex series of treatment processes at the same time. So as I mentioned, I often kind of think of them as being a very simple technology. They're basically just a big hole, and then maybe you got some mixers in there or something. But really, they are combining a number of different processes together, all into one very large reactor. They act as a clarifier. They're settling out solids over time. They are a bioreactor, particularly the aerated ones. They're there to actually grow some biomass and do some treatment. And of course, in a lot of cases, they are also serving as a digester. When those solids settle out, they can form an anaerobic zone across the bottom of the lagoon, and then therefore you can get some solids, digestion there happening too. A lot of lagoons undergo periodic dredging to remove the solids, if that is a key part of what that lagoon is supposed to be doing. You might find that would be something that happens every 6 months or a year or a couple of years, where the solids have to be removed, because usually over time they're going to accumulate. So you want to be able to get them out of there somewhat frequently. The other key thing that we have found, of course, when you are trying to do modeling is you need a lot of data, and frequently there's not very much data collected around the lagoons themselves. So, for example, most of the projects that I have worked on, if we have any data at all, it will be just on what goes in and what comes out. There will be very little information about, what the flow path is through the system, what the DO might be at various points, or any of the other concentrations that you would have. So, as I mentioned, they can act like very large bioreactors, but they're very much not mixed, not fully mixed. They're not one giant CSTR like you might imagine. So, they're very often plug flow in nature and can have very complex and very dynamic flow paths through the system from the influent to the effluent. So, this diagram here, this picture here, is actually of the lagoon that we're going to be talking about in the case study. And as you can see, it's asymmetrical, and the flow kind of comes in one corner and goes out another corner. And so, what is the exact way that everything flows through here? We don't really know that. So these are things that we're going to have to determine and make some judgment about, or make some assumptions about how things move through the system. Now, this one is showing here that they obviously have surface mechanical aeration. We can see them throwing the water out across there to get the oxygen entrained into the liquid. There are also other mixers here. So you may find some lagoons have this, some of them don't. Some of them might have more complex systems. In a lot of places, you may have just passive gas transfer. It's just a big, open, quiet surface that, does allow some oxygen transfer, but probably minimal in most cases. For systems that have engineered aeration systems, there is a wide range of different technologies that are out there to do that. So, as I mentioned, these floating, they're often anchored in place, but they're floating mechanical aerators and or mixers that you might have. That's there to obviously aerate the system, but also to provide some control or maybe help move the solids along, or help encourage a recycle where you're going to be bringing back some of that biomass that you might be growing. And I've also seen other systems that were even more like a conventional bioreactor and less like a natural lagoon, where there's submerged diffused aerators. You might have a big manifold all the way down the one side of the lagoon, and you'll have drop pipes that run down and across the length and the width of the lagoon itself. And I've seen something as simple as very inexpensive, PVC with holes drilled in the pipe, lowered into the system, all the way up to, proper, fine bubble diffusers as well. So there is a very wide range of different levels of complexity and different levels of engineering approaches to aerating your lagoons. So in addition to all of that, the solids can settle out and form an anaerobic layer at the bottom of the lagoon. So that is, possibly that's intended. Maybe the lagoon is there to actually do that final solid settling and remove that last little bit of TSS. Or maybe you don't want that to happen in your lagoon, so you got to have lots of aeration to prevent your biomass from settling out. But either way, you could have theoretically a lot of solids accumulating on the bottom. And so therefore, that needs to be part of what we're going to capture in the model. There's often, too, a significant thermal gradient from the surface, the top of the lagoon, like where it's adjacent to the atmosphere, through down to the depth of the water, all the way down to the bottom where the solids are accumulating. And by thermal gradient, I mean that in places where the temperature changes quite a bit during the year, such as like it does here in Canada where we are, you may find that in the summer when it's very warm out and you have a lot of sun beating down on the top of the lagoon, you may find that the temperature of the lagoon at the very surface is quite a bit warmer than the liquid that's farther down at the bottom of the lagoon where it's going to be cooler. And this can lead in and of itself to problems with what they call turnover, which is that you have an inversion of that gradient at some point during the year, often it's going to be in the fall or the early winter, when the liquid that's on the top is being exposed to the colder and colder and colder atmosphere, that it will eventually become colder than what is underneath. And then therefore that denser water is going to fall down. And sometimes that can be a big problem where you end up sort of stirring up and resuspending a lot of the solids that had been settled out previously. Now, that's a really difficult thing to capture in a model, but it is a particular sort of discrete event that can sometimes happen in a lagoon. So, and so that kind of thermal gradient can be an interesting aspect. Okay, so those are some of the relevant things that are happening around the idea of using a lagoon for treatment. And so what I'm going to cover next is all of the important processes that we need to capture into the model. And then we'll talk about how you actually model those in GPSX. So the things that we want to capture are, well, very obviously all of the flow as it goes into and out of your lagoon. So we'll have something coming in, we'll have flow as it makes its way through. And as you'll see in a later part of the presentation, deciding how that flow moves is sometimes very challenging. And then we have the effluent obviously leaving. But another important factor that can come into play with a lot of lagoons is this sort of element of backmixing. So in a lot of places, there's a resuspension of the solids potentially, or at least carrying the solids back as it moves around in the system. It is often a very difficult thing to quantify with a measurement, but the modeling will indicate that, yeah, there is some backmixing going on because we are seeing the biomass be present in some of those earlier upstream systems. So generally, that is one of the approaches that we find that we have to take is that you have downward flow, but with some backmixing. Another thing that we need to take into account and capture in the model, of course, is gas transfer. So in both directions. Now, in a place where you have aeration going on, you're definitely going to want to specify that happening in each one of the reactors that you're using to describe your lagoon. So that's entraining air and getting oxygen into the system, but also a gas transfer in the other direction for the release of the gases that might be happening as a part of, the biological activity and, release of CO2 and methane if we're doing some digestion of solids as it moves. We also are going to want to capture all the solids that are settling. So all the solids that are coming in, that are accumulating along the bottom. As I mentioned earlier, we want to make sure that that mass balance is captured properly as well. And then lastly, of course, we have the biological activity. And this is where specifying how you are going to divide up your lagoon into reactors becomes relevant. Now, what we want to do, of course, is figure out what part of the lagoon is going to be in each kind of condition. So we can assume generally, almost always, that there is at least some of it is going to be interacting with the air. There's going to be some aerobic zone very much near the top. And then some portion of the lagoon is going to be anaerobic. Now, of course, if you had a lot of mechanical mixers or other types of aeration system in there, it might be almost fully aerobic and maybe just a tiny little anaerobic piece along the bottom. So therefore, you kind of have to tailor your approach depending on what technology is being done, with the depth of the lagoon, how it's designed, and so on. It can be really challenging, actually, and there's a lot of places, too, where you can have significant aeration that comes from just wind blowing across the surface and causing some turbulence there. I've seen a couple places where we had to deal with that. So therefore, you would have some sort of aerobic zone and some sort of anoxic, and maybe, we don't really know what portion of that is there, and maybe there's some sort of partially aerated zone in between. It can be very challenging to figure out how to handle that in the best way. Excuse me. So what it boils down to is figuring out what kind of zone that your system is probably most made up by, and then being able to model it in that entire section as one completely mixed zone. And so therefore, for the example that we're going to be showing you, they had, as you saw in the earlier photographs, they had mechanical mixers. So there were many places where we knew it's going to be mostly a fully aerobic zone. So therefore, you can model it in that way. But you may need to make different assumptions for whatever lagoon it is that you're trying to do. So once you kind of have a bit of a handle around what your system is designed to do, what it's supposed to be. Is it supposed to be a completely anaerobic system or not? You are then going to want to break down the lagoon itself into a series of completely mixed reactors that are in parallel or in series, depending on how the flow moves through the system. Now, fortunately, this is a really simple one, and I've actually had a couple of projects that worked like this, where there were lagoons, but they were very long and skinny, and we could basically know and understand that the flow came in one end and went out the other. So therefore, we knew that was 4 zones in series. So that was a pretty straightforwardly easy one to do. You can just repeat that, and then you can say we know the flow moves along, and we might have a little bit of backmixing happening there as well. But in general, that's kind of an easy, really straightforward one, not too difficult to set that one up. And it would generally look like this in GPSX on the drawing board. So we have rows here that are in parallel. We have 4 zones in series, and then this pumping section here, going back to the previous zone, is how you do that backmixing. And the ratio of forward flow to how much you backmix is, well, that's probably part of the calibration itself, right? So you would start out with something, see if that works, and then maybe you have to make adjustments to those flows. A lot of our experience has been that the backmixing is generally equal to or less than what you would find in that forward flow. Now, in this particular system, you can see that we're going to assume that when it gets down to the end, that all of that flows out. So we're not settling out any solids in this particular case. That was completely suspended system. So I'll come back to talking about solids in a minute. It becomes far more challenging, however, when you need to break down a lagoon that looks like this, especially if you have a flow that comes in some place, spreads out in some maybe not really well understood way, and then leaves. There, you can break it into CSTRs, but now it's not nearly as clear as which way the flow moves around. And often it seems that it's not quite even as symmetrical as this looks. You may find something comes in the corner or comes in one side and goes out the top or something like that. So often it is a big question mark. Exactly how does the flow move through this system? So that is where the challenge comes in, to find out as much information as you can. Now, in a perfect world, if you had a lot of budget, you could probably do CFD analysis on this to figure that out, or you could do a tracer study. Try to find out a little bit about how these things fit together. But in a lot of cases, that's not information that is going to be easily available to you. And what we recommend, and what has worked well for us, is to talk to the people on the ground, talk to the operators who work with these systems, and get an understanding of what was it designed to do originally, and how is it being operated now, and what is your understanding of how all the flow moves through this system. What do you see with accumulation of solids? Does it happen mostly on the sides or in the middle? Do you know that there's some shortcutting that you might see happening in the winter if you've got some ice on it or something like that? Those are all things that you can use as sort of clues to look into understanding which way the flow moves around. But there's no question that you might have to take a couple of shots at this, try to put it out into a way that makes some sense to you, see if you can calibrate to the data you have, and if it doesn't work, then probably you're going to have to go back and iterate around a couple times to get it right. So as I mentioned, really we ask a lot of questions when it comes to putting a lagoon model together, a lot of questions of the people who are running that lagoon in order to understand how it fits together. There are places where there's big baffles and recycle pumps and mixers and other things that are there deliberately to make it move in a certain kind of way. So that would be key information that you should definitely need to know. Some of the decision about how to divide it up will also be driven about the need to try and find those aerated and non-aerated zones. So clearly, if you're having a large mechanical aerator, like we'll show in our case study here shortly, that zone is going to be obviously aerated from some area right near where that mixer or that aerator is. So therefore, that particular CSTR is probably going to be in an aerated zone. So you might use that information about the location of where all the aerators are, or the diffused air system, or whatever it is, in order to help divide up which way you want to do the CSTRs. That's really not any different at all than setting up a BNR system where you've got an anaerobic zone and an oxic zone and an aerated zone, and you kind of divide up those tank sizes accordingly so that you can make sure that you've got the aeration in the right parts of your plug flow system. And as I mentioned, iteration is often part of it. In a lot of full-scale regular BNR systems, you'll say, hey, just tell me what your tank size is. Here, you might not know that, and you might have to make a couple of iterations to lay out the way that it works. Now, a lot of ponds, as I mentioned when I was talking about dredging, they have solids removal as a significant part of the process that they are trying to do. So now that example that I showed you earlier with the 4 lagoons and those 4 rows of CSTRs in parallel, I didn't have any solid separation handling there, but it is often an important part of the lagoon. So therefore, you need to capture that in the model as well. And generally, you could do it with a clarifier, but in reality, I think it's easiest to just stick with something simpler and use an empirical solid separation unit, like our black and blue dewatering unit, in order to concentrate the solids and remove them out of the system. So what you may find is you've got this series of CSTRs, and you're going to sprinkle a couple of dewatering units in there with the empirical model to concentrate those solids and get them out. Now, when we're doing that kind of dredging activity, that makes it kind of a discrete solids removal event. But in order to be able to run your model for steady state, you're going to want to make the steady state approximation of that. So if I know that I'm taking, X ton of solids out of the lagoon once every 6 months, what you need to do is probably find out the right flow rate so that you can just stretch that out and have one continuous flow that does that same amount of solids removal. Okay, so this is what that would look like. You would have, your CSTRs that represent the different zones of the lagoon, and then you might have a solid settling unit removing those solids. And I suggest using the empirical model here. You're going to capture, say, 99% of the solids. You can figure out an appropriate flow rate, or you can set the concentration of what that would be, and it'll figure out the flow rate for you. So that idea of just making sure that you get the correct amount of solids removed such that you get the right solids in your effluent. Okay. So combining all of those concepts together, as you can see, of course, the application of these various modeling techniques is really site-specific. It depends a lot on how the lagoon itself was designed. Is it supposed to be doing solids removal? Is it just a polishing thing? Is it really just like a storage unit? It doesn't really do any treatment? Those are important questions to understand. And really, it's the lack of information about flow that I have always found to be the most challenging thing to deal with in the lagoon. So we always suggest speaking with the operators, speaking with the facility owners and operators to understand what was it designed to do and what is it currently doing, and what is your experience shown with what you know about how that lagoon works. Okay, so what we're going to do now is I'm going to pass things over to Dan so that she can talk about the Langley project. And then what we'll do is after she's described all that and gone through those results, we're gonna actually show you some modeling results that came out of that. We'll come back and we'll talk a little bit more and wind kind of things up, and then we'll talk a little bit about some questions that you might have. Okay, Dan, I'm passing it over to you.
Okay, thank you, Spencer. So today I'm going to talk about a case study. We did on the Northwest Langley wastewater treatment plant in Langley, British Columbia, here in Canada. This is a secondary treatment facility that has a treatment capacity of 23,000 meter cubes per day. And the annual average as of 2018 was 13,300 meter cubes per day. And in this case study, we are only focusing on the lagoon system that's downstream of the fine screens and upstream of the trickling filters. So before modeling the lagoon system, there are a few questions that need to be addressed. The first and foremost is, how does the wastewater flow within the lagoon? As Spencer mentioned before, lagoons may have quite complex and dynamic flow paths, but very often than not, they don't have sufficient data collected on the flow within the system. And this is especially true in this case study, since we don't have the resources and time to do experiments such as the tracer testing or computational fluid dynamics, we have to rely on the operator's experience on determining the flow pattern. The second question is, how should we divide the lagoon? We don't want to have too few zones that restrict our ability to model complex flow patterns. But at the same time, we don't want to have too many zones that further complicate the already complicated problem. So there is a fine balance that we need to find. The next question is regarding the backmixings and recycles. Are we going to model any backmixings and recycles? And where should we add those backmixings and recycles? The last question is, how should we adjust the oxygen transfers? The Langley wastewater treatment plant uses floating mechanical aerators. So we should expect that the oxygen transfer rate to be higher in the area adjacent to the aerators. And as you move away from the aerators, the oxygen transfer rate should be lower. So these are some of the questions that we need to answer when modeling the lagoon system. On the right-hand side here is a blown-up Google image of the lagoon. The influent comes into the lagoon at two different locations on the bottom of this diagram, and it exits through the top right corner here. The surface aerators and mixers are also marked on this diagram. So to answer the first question that we had regarding the flow path, we learned from the operators that the flow is clockwise within the lagoon. And based on that information and the location of the aerators, we divided the lagoon into 8 zones. These zones were of various sizes, but we tried to have each zone centered around an aerator. We also included non-aerated zones, such as zone number 2 and 7, so that we have the combination of aerobic and anaerobic zones in the lagoon. Regarding the backmixings and recycles, since the wastewater flows clockwise, creating a recirculation in the lagoon, so we feel that there isn't really a need to add additional recycles. But we did have a backmixing from zone number 3 to zone number 2 due to the aerator pushing the wastewater away. So based on all the information that I just talked about, the flow pattern was determined as shown in this diagram here. It's worth mentioning that the length of the arrow is proportionate to the flow. So we implemented the flow pattern in the previous slide in the GPSX, and here's the GPSX layout. The influent wastewater goes into zone number 1 and 4 and exits from zone number 8 to the trickling filter. As mentioned before, a backmixing from zone number 3 to 2 was included. It's not shown on this diagram, but it's inside this plug flow object. So several assumptions had to be made during this modeling exercise. For example, the surface area of each zone was estimated based on that satellite image. A tank depth of 4.5 meters was used based on the information from the hydraulic profile. The initial backmix ratio was assumed to be 1:1. This backmix ratio is the backmixing flow, which is from zone 3 to zone 2, relative to the influent flow going into zone 2. We also assume that the locations of the aerators stayed the same during this calibration period. So after the model was set up, the first step in calibrating the model was to characterize the influent. The plant actually had a quite extensive sampling program, and we got a lot of data to calibrate with. The parameters that we changed in the influent characterization is listed here in this table. We used the 2018 annual average for the BSS to TSS ratio. And to match the soluble BOD and the soluble COD data, we reduced the default BOD to COD ratio by approximately 15%. The default value here in GPSX is the typical value for typical municipal wastewater. Now we can finally answer the last question about the oxygen transfer. So the typical alpha factor for a mechanical aerator is around 0.9. But to account for the reduced average oxygen transfer rate across the entire zone, this number was reduced to 0.8. We also reduced the anoxic reduction factor for denitrification on nitrite, because as you see in the results in the next slide, their nitrite is quite high in the summer month. So using a lower value here could prevent the heterotrophs from denitrifying all the nitrite directly. The maximum growth rate for AOBs was reduced to 0.8, so that in the winter month, the lagoon effluent ammonia could be higher to match their data. We also found out that the nitrifiers were quite sensitive to the temperature. So we increased the temperature sensitivity of the AOB maximum growth rate. The calibration was done using the 2018 data. And in this dynamic calibration, the model read in the data for influent COD, TKN, and ammonia. So we're only showing the results for TSS, VSS, and BOD here. In these two graphs, the dots are the data we're comparing to, and the solid lines are the model predictions. So as you can see, that the model predictions match the data very well. So we have done a pretty good job on the influent characterization. And this slide shows the 2018 simulation results for the lagoon effluent. In the first graph here, the black line shows the ammonia concentration. The red one is the nitrite, and blue is nitrate. As we discussed earlier, the nitrifiers are quite sensitive to temperatures. So in the summer, we see that the lagoon removes the ammonia nicely, but in the winter, there isn't much activity going on, and the ammonia is hardly removed at all. So the model was able to predict this behavior reasonably well, although towards the end of the simulation, the ammonia didn't spike again like shown in the data. And we think this might be due to the relocation of the aerators. In terms of the nitrite, we see a very high level of nitrite in the summer month. And this is commonly referred to as nitrite lock, which is the inhibition of nitrite oxidizers from nitrite. And this model was able to capture the circulation of nitrite in summer. However, the model failed to capture the spikes in the nitrate, and it overpredicted the denitrification, which can also be seen on this graph about alkalinity. Since you can see there's a very high level of alkalinity in the summer. We also did another validation run using 2019 data just to see how well the predictions fit the data. And it turned out to be quite good. Although the ammonia concentrations were underpredicted in some period of time, the model successfully predicted the spikes in the nitrite and nitrate. The alkalinity data actually matched pretty well compared to the 2018 simulation results. So just to conclude, modeling lagoons usually involves a lot of uncertainties, such as determining the flow pattern within the lagoon, adding back mixings and recycles, and also determining the oxygen transfer rate. So when there is a lack of information, we need to make appropriate assumptions. And as this case study demonstrates, despite those uncertainties, the calibrated lagoon model can still reasonably predict the performance. And to improve the calibration, it would require further experiments to be conducted, such as a tracer testing or CFD. So with that, I'm going to pass it over to Spencer to summarize the webinar.
Thank you, Dan. Okay, so we are back to the webinar slides. So just to add a couple thoughts to Dan's case study analysis there, it was a really interesting and challenging project to work on, but it was really interesting how we were able to capture that behavior, particularly as we were coming out of the winter and into the spring, and we had the loss of, the nitrification started up, but capturing that accumulation and abundance of nitrate there. So that was a really interesting part of how our Mantis 2 biological model arranged into those kinds of CSTRs in parallel and in series can work to actually do that. And it did a good job of helping the client analyze what it was that they wanted to do with this system. So just in summary, talking about all of those methodologies that we presented earlier, and as you saw them applied in our case studies, Lagoons certainly can be a challenging process to simulate, and given that lack of information. So, but the approach is generally to break the system into CSTRs. Some of them will be aerated and some not, and whatever is appropriate for your particular system. And that little challenge of trying to find out which way they go together, where does potential recycles happen, and so on, that can give you a decent approximation. You won't be able to get it perfect, and it's very rare that you can actually model anything to perfection. Of course, even the full-scale systems that exactly what the volumes are of the tanks. But the idea is that you can get a very good approximation if you know a little bit about how the flow moves through the lagoon. So don't be afraid to have to iterate and make changes to the way that you've hooked your CSTRs together in order to see whether that actually gives you a better fit to your data that you have.